Okay, so we're on page 457 of your Absolute Value Math 20 workbook, and today we're looking at solving absolute value equations, part 1. Of course, an absolute value equation makes sense. It's got absolute value bars, and it's got a left side and a right side, which makes it an equation. So we're going to be looking at not only how to solve graphically, but also how to solve algebraically. So graphically, of course, using your you can be using your graphing calculator. A great way to check your work. Algebraically, of course, important if we're looking for exact values or if you're needing a complete solution. So taking a look at the very first question, we've got absolute value of 2x plus 3 is equal to 8, and so we know that using our graphing calculator we can essentially solve any equation we've got because we recognize that left side equals right side for an equation, and so all we need to do then is to enter in y1 is equal to the left side and y2 equals to the right side, and then find out what those points of intersection are that would make that equation true and balanced. So remember to get the absolute value bars. You can go to the math button on your TI calculator, and across the top you'll see number, the number menu if you scroll over to the side there, and I believe it's the first option is the absolute value bars that you'll see. So absolute value of 2x plus 3 is y1 and y2 is equal to 8. So if you enter those in, there's my y2, which is my horizontal line of y equals 8. And the absolute value of 2x plus 3, of course, we've got, it's got that piecewise function part that we talked about last class. So the right side of this looks like the graph of y equals 2x plus 3, and this arm on the left is actually negative 2x minus 3, and with that kind of reflection point at negative 3/2. So that's, if we were to talk about our piecewise function, we would say for that interval or the domain of x less than negative 3/2, the graph looks like negative 2x minus 3, and for the domain, the subdomain of x greater than negative 3/2, we've got the graph that looks just like y equals 2x plus 3. So now that we've got those graphed, we can use the intersect feature. So second, calculate intersect, which is the fifth option on your TI calculator, and we would find that our x values are negative 11/2 and 5/2. Of course, I'm not interested in the y values because my equation itself is just to solve for x. So the other method is to look at the x-intercept method. So this is kind of similar to solving equations where we're going to set it to 0. So rather than absolute value of 2x plus 3 equals 8, we'll subtract 8 from both sides so that the right side ends up being 0. So we've got absolute value of 2x plus 3 minus 8 equals 0. And so you just would enter in that left side, which we've got as y1, and with this particular case then we would use the 0 function because that is finding out what these two x-intercepts are. And you can see when we compare those graphs, literally what are we doing is we're just translating that whole absolute value function down 8 units. And of course when we use the 0 function on our calculator in that calculate menu, of course we find out that these x-intercepts here that I've indicated are exactly the same as above, negative 11/2 and 5/2. Awesome. Okay, let's take a look then. So just go ahead and hit pause. Try this on your own through graphing, and I've done them using left side and right side. You might also try them by setting it to 0 and trying using the 0 method. So just hit pause and come up with your graphs and your answers, and then we'll come back and compare. Okay, so in my first graph, I've got the left side, absolute value 3 plus x is this green function right here. And you can see again that piecewise function with our subdomains happening at that x-intercept of -3. So when x is less than -3, the graph looks like a negative slope, so it's negative x minus 3. And on that subdomain, when x is greater than -3, then our graph sure looks like 3 plus x or x plus 3. And then our other line is y equals 2x plus 1. You can see that there's one intersection and so one solution, and are using that graphing function to calculate the intersection, we would have x equals 2. For the second one, x absolute value of x squared minus 17. So if we take a look, if we were to just graph x squared minus 17, we know it's a quadratic. It would come all the way down like so with that y-intercept of -17. But because it's an absolute value, then it essentially reflects everything that is below our x-axis is essentially reflecting above into quadrants 1 and 2. And so that vertex that was -17 is now at +17. And when we draw our line y equals 8 across, we can see 4 intersections. And so yes, that's using your calculator 4 times to calculate those 4 intersection points. And you would see that come up as x equals -5, -3, +3, and +5. We could also write that as x equals ±3 and ±5 as well. Okay, so to determine how to do this algebraically, all the steps are here, so you can take a moment and read that through. But to me, I don't need to read this to you. I think the best bet is for us to go through and to try it as I'm explaining it. You might hit pause and go back and take a look at the notes that they've got as well. Okay, so we've got the equation absolute value of 2x plus 3 is equal to 8, and this was the graph. That was the very first equation that we graphed on the previous page. So to figure out what our subdomains are, like where does that random -3 halves come from, is of course what we're trying to figure out is if I was graphing absolute value of 2x plus 3, where does that hit the x-axis? So of course we're talking about that x-intercept. So 2x plus 3 then is equal to 0, or 2x is equal to is equal to -3, and so x is equal to -3 halves. So that's where that is coming from right here. Myself personally, I find it really helpful just to do a little bit of a sketch right here of what that graph is going to look like, that absolute value of 2x plus 3, so that we can see that in the subdomain when x is less than -3 halves, what's happening here is that the line is taking on a negative slope, which means that it's going to take on the negative version of 2x plus 3, or negative of 2x plus 3, also known as -2x minus 3 equals to 8. And on the right side, this other subdomain, we've got x greater than or equal to -3 halves, and so you can see here we've got the positive slope, so then we're just taking the positive version of 2x plus 3, which is of course itself. So let's go through and we'll solve both equations then. And so in this case, we've got -2x is equal to 11, and divide both sides by -2, so x is equal to -11 halves. On the right side, subtracting 3, so 2x is equal to 5, and x is equal to 5 halves. The nice thing about this is we could do a check, but the only check that we really need to do is to ask ourselves, is negative 11 halves within the subdomain which is less than negative 3 halves? Yes, negative 11 halves is less than negative 3 halves. So is the solution in the subdomain for this side? It is yes. For x equals 5 halves, is 5 halves greater than or equal to negative 3 halves? And the answer is also yes. And so we recognize that we've got two solutions. So the answer is x equals negative 11 halves and x is equal to 5 halves. Okay, so that's a nice piece for that verification. We don't actually have to do a full left side, right side check. If we're fully certain that our subdomains are correct, then we can just check whether our solutions fall within the subdomains. Okay, let's take a look at Haley's solution for the next graph, which was the absolute value of 3 plus x equals 2x plus 1. So to determine those subdomains, what am I ultimately looking for? People get confused. Well, do I want the x-intercept of that left side or the right side? Ultimately, we're looking at the one, the subdomains are created by the absolute value functions. So that's what we're concerned about. So 3 plus x equal to 0, which means that x is equal to negative 3. So that is what's going to define our subdomain. Again, I'm going to sketch my little graph. That absolute value of 3 plus x is going to look something like this. So on the left side of that negative 3, we've got x less than negative 3. On the right side, our subdomain is then x is greater than or equal to negative 3. Again, the question comes up as to, well, what about that equal to? Why is one equal to the other not equal to? Well, we want to have that negative 3. It has to be in one side or the other, otherwise we would have a null point right there, an open circle, so it has to belong to one of them. And so typically speaking, we go on to that positive side of things. So if we take a look on the left side then, again, if we refer to our little sketch, we can see that in the subdomain, when x is less than negative 3, we've got a negative slope. So if that's a negative slope, then I'm looking for the negative version of 3 plus x and equal to 2x plus 1. And so we can go ahead and solve that on the right side of that subdomain. So when x is greater than or equal to negative 3, the slope is positive, so it's just the positive of that, which is simply 3 plus x is equal to 2x plus 1. So go ahead, hit pause, and see if you can figure out what those two solutions are and whether or not they belong within the subdomain, and that will define what our solution or solutions are. Okay, so when we take a look at that, on the left side, in that subdomain x less than negative 3, we get x equals negative 4/3. Is negative 4/3 within that subdomain less than negative 3? No, negative 4/3 is not less than negative 3. And so is a solution in the subdomain? The answer to that would be no. Oops, not sure why that. And then on the right side is 2 within the subdomain of x greater than or equal to negative 3. So 2 is greater than negative 3. So that is a yes, which tells us that our solution is x equals to 2. So before moving on, though, I want to be clear as to what is this negative 4/3 representing. So why does that not actually work? So if we go back up to the graph of this particular question. So there it is in this example 1a, the absolute value of 3 plus x equals 2x plus 1. So remember, we're looking at the subdomain when x is less than -3. So this green arm right here. So remember, that particular equation was -x minus 3 equals 2x plus 1. Whoa. And so really, what is that describing is -x minus 3 would be if this particular line was to continue on, because remember, this equation right here, -x minus 3 equals 2x plus 1, doesn't have absolute value bars on it. It's simply, hey, the line -x minus 3 that goes continuously in both directions, and the line of 2x plus 1 that goes continuously in both directions. Here is that intersection point, and that is -4/3. So that intersection point does exist between -x minus 3 and 2x plus 1. However, this particular point right there, let me use a different color, is not actually on the graph of the absolute value of 3 plus x with 2x plus 1. So we would call that, essentially, that's an extraneous solution. That solution does not actually exist because it's not part of that absolute value graph. And so that's where that -4/3 is coming from. Okay, so let's take a look at another way of going through this particular one. So an alternative method. So this one a lot of people actually quite like. I think there's advantages and disadvantages to it. I think it's a lot of people understand this way better. However, it's a little bit more work because you have to essentially check or verify every single one. So essentially, this particular method of going through it is essentially looking at all of the possible what ifs. So we are essentially saying, hey, absolute value of 3 plus x as a piecewise expression we know is going to be then, it could be -x minus 3 when x is less than -3, and it could be x plus 3 or 3 plus x when x is greater than or equal to -3. So when we look at that then, what we're just going to do is we're going to take all of those, and I should, write out that this is taking it from the absolute value of x plus 3, and those are our two versions then. So at the end of the day, we're going to just try both of them. So we're going to take a look at -x minus 3 equal to 2x plus 1 and solve that. And we're also going to take a look at x plus 3 and equal to 2x plus 1 and solve that. So let's take a look. So I'll just do the positive one here first. And so again, 3 is equal to subtracting x, so x plus 1, and subtract 1, so x is equal to 2. However, because I don't have subdomains in this particular method, I actually have to go through and verify. So when I verify, I'm going to verify in the original absolute value equation. So when I verify x is equal to 2, so my left side is then equal to the absolute value of 3 plus 2, which is the absolute value of 5, which is simply 5. On the right side, I have 2 times 2 plus 1, or 4 plus 1, which is 5. So left side equals right side, and so then that tells me that x equals 2 is a solution. So on this particular case, then we're going to add x to each side, so -3 is equal to 3x plus 1, subtract 1 is negative 4 is equal to 3x. Divide by 3, so x is equal to negative 4/3. So now if I verify x equals negative 4/3 in my original equation, then on my left side I have the absolute value of 3 plus negative 4/3, and that is going to be, so 3 is the same as 9/3 plus negative 4/3 is then going to be 5/3. Absolute value of that, which is of course simply 5/3. And then on my right side I have 2 times negative 4/3 plus 1, so that is negative 8/3 plus 1 or plus 3 over 3, which is negative 5/3. And positive 5/3 does not equal negative 5/3, so that solution needs to be rejected. So here, left side not equal to right side, so this one has to be rejected. Okay, so comparing this method, obviously we're getting the same answer, which is the solution that x is equal to 2, but it's just a little bit longer because we have to do a full, complete left side, right side verification on these. Okay, so in this particular case, for class example number 5, we're looking at the absolute value of x squared minus 9 equals 7, and so if we solve by graphing, what do we know is that the graph of x squared minus 9 typically is going to look something like this, with our y-intercept of negative 9. However, since instead it is the absolute value, then what happens is everything that is below our x-axis is going to reflect into quadrants 1 and 2, and so in fact the graph of the absolute value of x squared minus 9 then takes on that kind of funny W shape again. And so this is y equals absolute value of x squared minus 9. That is that one. And then y is equal to 7 is then going to be a horizontal line because this we know is 9. Then that means that 7 is going to end up going across right here. And this is y equals 7. So we should see here then that there are 4 solutions, and if you put that into your calculator, then you would actually see those values, and we end up in fact with decimal approximation for 2 of them. So we've got plus or minus 1.41 approximately, and the other one is plus or minus 4 as well. Oops. Okay, so not fond of that plus or minus 1.41 because that is obviously a decimal approximation. So looking at that algebraically, for this quadratic we can't go piecewise. In this particular case we're simply just going to look at the verification piece. So we've got either we're looking at the positive, which is x squared minus 9 is equal to 7, or else we're looking at that negative. Remember that little hump in that middle is based on the equation of negative x squared plus 9, and that is then equal to 7. So let's go ahead and solve that. So this first equation add 9 to both sides, so x squared is equal to 16. So that's where we get our x is equal to plus or minus 4. And then in this particular case, um, negative x squared, is equal to negative 2. Divide both sides by negative 1, of course, so x squared is equal to positive 2, so x is equal to plus or minus the square root of 2. So that explains that plus or minus 1.41 then. So just to go through our verification, so if we're verifying and a bit of a pain, but we have 4 verifications to do. So if we verify x is equal to negative 4, back into that original equation, so absolute value of negative 4 squared minus 9 is on the left side. So I should write LS is equal to, and so then that is the absolute value of 16 minus 9, so absolute value of 7, which is of course 7, which is also equal to the right side. So that's good to go. So if we verify x is equal to 4, then the same thing is going to happen because we're going to square 4, 16 minus 9, which is again absolute value of 7, which is 7, which is our right side. So that's all good. If we take x is equal to negative root 2, then our left side is, oops, I'm missing my equal sign there. So my left side is equal to the absolute value of the square negative root 2 all squared minus 9, and negative root 2 squared is just 2. Subtract 9 is negative 7, but it is the absolute value of negative 7, which is of course just positive 7, and so that is also again equal to our right side, and we already know that that's definitely going to happen again for when we verify x is equal to positive root 2. Our left side is the absolute value of positive root 2 squared minus 9, and root 2 squared is simply 2 minus 9, again negative 7, but the absolute value of it is positive 7, which is equal to our right side. So there we have it. We've got our 4 solutions, which are x equals plus or minus root 2 and plus or minus 4 in this particular case, and this is also a great example to show you why algebraically is going to give us our exact answers when decimal approximations will happen within our graph. So thank you for listening in, and let me know if you have any particular questions.